On this computer. Okay. Yeah, so I think we can begin. Right. Today, my plan was to discuss another thing that's pretty important, which is a specific as another type of relation. Okay, so these are called order relations or posets. So maybe we can discuss that. So, like, most of the time we have spent talking about equivalence relations. So you should think about of this type of just a different kind. Okay. So the idea is that these are actually like the analogs of like the greater or equal relation that between numbers. So this is like a kind of relation. So this is a type of relation. That generalizes the greater or the greater or equal or less or equal, strictly less or greater or equal or strictly greater relations. And so by that I mean, like, you have, I mean, everyone has seen something like when you write like x is less or equal to y, right? So you can think of this as being a relation. So this is like gives a relation where x is related to y if and only if x is less or equal to y. Okay. So what sort of properties would this have? Like, let's just think about like this particular example to see what could we extract, right? So we all know, right, what properties can we expect? Oh, maybe someone wants to give some suggestions, right? Like, so what's a important property of this symbol less or equal to? Anyone can think of it? What's something important about what's an important characteristic of this symbol? I don't know if the question makes a lot of sense, but let me give you a couple of seconds to think about it. Well, x could equal y. That's true. Yeah, so that means that it could be reflexive, right? I mean, let's think about it that way, because you do know that, like, is less or equal to reflexive, right? Because, well, we know that x is less or equal to x, right? So this one should be true, right? What about symmetry? Would this be right? Well, let's think about it. Definitely, it shouldn't be symmetric, right? Let's think about symmetry. So, for example, we know that 1 is less or equal to 2, right? But it is not true that 2 is less or equal to 1, right? So this, in general, I mean, this cannot be expected to fail. I mean, this will fail in general, right? So this will fail. So how about transitivity? Because someone mentioned that, right? So what can we say about transitivity? So what if you know that x is less or equal to y and y is less or equal to z, right? What can you say in this case? It does follow like from how this relation between ordering or of numbers, that it does follow that x is less or equal to z, right? So okay, so transitivity should also be fine. So like, if we compare this with an equivalence relation, like reflexive is still true, symmetry is no longer true, transitivity is true, right? So two of the three. So by comparison, right? So this differs from an equivalence relation, right? Because we no longer have symmetry. Right? So in fact, what it's done is that instead of asking for symmetry, we ask for something that's called anti-symmetry or anti-symmetric. So instead, like what we do, I mean, because an equivalence relation had three properties. So here we're finding, like we're trying to find something with three properties. So reflexivity we have, transitivity we have, and now we're trying to replace symmetry with something else, and that something else is called anti-symmetric. So, like before telling you what it says in general, let's just think about this case. Imagine that you had x is less or equal to y, and y is less or equal to x. What could you conclude if this happens? If you have two numbers for which this holds, what can you say? Yeah, that x is just y, right? Good. And so that's like basically the generalization. Like what I'm about to write is like the generalization of these three properties of like less or equal. And whenever like a relation has these three properties, it will be called like an ordering relation. Okay, so let me give you the definition. And you see like why it should be thought of as an ordering, uh, because like it would have the same, like what you would think of as the three properties that it characterizes like less or equal to among numbers. So like a relation R on a set A is called an ordering relation if it satisfies what? Well, the first one we already said that, like the reflexivity, which we know from before. Reflexivity, which was that for every x in A, x is related to x, right? The transitivity that we also have seen before, right? That for every x, y, z in A, if x is related to y and y is related to z, then x is related to z. And the last one, which I'll use with a different color because it's a new one, which is called the antisymmetry. Or antisymmetric. Which is that for every x and y in A, if x is related to y and y is related to x, then x equals y. Okay, so this is a new, like like, so basically, if you replace antisymmetry with symmetry, you get an equivalence relation. And if you use antisymmetry, you have like this ordering relation. Is that making sense? So, and the set A together with this relation is called a poset. Poset stands here for partially ordered set. So this is what this means. Well, let me give you a second to copy this. I'll give you some examples. But in the meantime, yeah, if there are any questions about this, let me know, or you can type it on the chat. So far, so good. Any questions about this? Let me box this again. Again, I'll upload the PDF to the Canvas announcement once we're done, as well as the video, obviously. Is this okay? Is everyone okay with this? Okay, so let me give you some examples. I mean, the obvious example is like the one that we started with. So let's think about some examples. The first one is like the canonic, like the basic example, which is like A to be the real numbers, and then you say that X is related to Y if and only if X is less or equal to Y. Right. So, I mean, we already like saw that this one works, right? Because this was like our model that we used to come up with this definition, right? So it's reflexive because it's X is less or equal to X. Transitive because that's how just like the ordering relation works about the numbers, and then antisymmetric, right? Because of what we had said. So far, so good. Now let's do another example, which is a little bit more interesting, which is, let's take our set to be the natural numbers, right? Let's, yeah, I guess, let's see. Yeah. And then let's say the two natural numbers are related. Let's call them N and M because that's more normal here when you're talking about natural numbers. That's a more common letters for natural numbers. We say that these two are related if and only if, well, I guess M comes before N. So M is related to N if and only if, well, let's call them A and B, sorry, too many. Let's keep it M and N. If and only if M divides N. Okay, so for example, 2 is related to 4, right? Since 2 divides 4, but 2 is not related to 3, right? Since 2 does not divide 3. And just as a reminder, what does it mean to say this means that, right, that n can be written as a product of m times, another integer. So let's call this other integer r for ratio, where r is another integer. In other words, n over m has to be an integer, which is r. Right. So why is this? Let's just check that whether or not this is like an ordering relation. And that kind of like, you should actually think of an ordering relation as giving some sense of like something being smaller or larger, right? And it does make sense to say that if 2 divides 4, there's like a sense in which 2 is smaller than 4, right? But it is like a more precise sense than just saying smaller, because like now we're saying that it appears as a factor of 4 when you decompose 4 as a product of integers, right? So let's just check that this is reflexive. Is it true that m is related to m, right? That means that m divides m. And that's true because m over m equals 1, which is an integer, right? I suppose here, like, just to avoid like silly cases, like just to make our life easier, when I think about the integers, let's just assume that none of them is 0, right? So here let's just exclude 0 for our mental sanity, like, so that you don't have to worry about division and things like that. Is that making sense? And then that's the first property. The other property that we had to check is transitivity, right? Well, but what is like, imagine that you have that m divides n and n divides l, right? So here, like, m divides n, here n divides l. So what does this mean here? That n over m is an integer. And what does the second one mean? It means that L over N is an integer, right? Just give me a second to open the door to my dog. Right, and so what do we want to know now? We want to know whether, what's the question for transitivity? We want to know if M divides L, right? So this is the question. So you have to look at L over M. And is there an easy way to see that that should be an integer? There's a trick, right, that you can use to show that this is an integer, which is? Any ideas? I mean, it's kind of obvious depending on how you think about it, right? But one way to think about this is that this is the same as you multiply and divide by n. right? So this is an integer. This is also another integer by hypothesis. And so the product of two integers is an integer, right? So this should be an integer as well. Is that making sense? And then for like the antisymmetry, right? If m is related to n and n is related to m, this one tells you that this means that m divides n, and this one tells you that n divides m. But I mean, I don't know if it's clear, right? For an integer to divide another integer, we're dealing with positive integers. So that means that m must be less or equal to n, and this one means that n must be less or equal to m, right? So the antisymmetry is just like a consequence of the antisymmetry for the usual less or equal property between numbers. Is that making sense? Any questions up to this point? So far, so good. So notice in particular that this like already tells you something important. Like here's an observation. For like real numbers, right? And for every x and y as a real number, right? It is always the case that either x is less or equal to y or y is less or equal to x, right? If you are given two numbers, right? One must be the largest of them, right? So for real numbers, x being less or equal to y would mean that x is related to y, or y being less or equal to x would mean that y is related to x, right? So like in the case of real numbers, like you can always compare to real numbers, right? So for real numbers, you can always compare two of them using this less or equal relation, right? But what about like the relation that we just introduced with the integers? For the integers, right? And that this divide and m is related to n if and only if m divides n. We already gave an example earlier that this is not necessarily true, right? We have that it is not the case that either m is related to n, or n is related to m. Right, like which two examples did we give? I gave an example earlier. What could you take m and n to be here, where this does not happen? Well, you could take 2 and 3, right? Because 2 is not related to 3, because 2 does not divide 3, and 3 is not related to 2, right? So that means that like when you're talking about division, it is not necessarily the case that you can under division, it's not always the case that two integers, one of the two has to divide the other. So like with this order or way to order the integers, you don't get like a linear order. I mean, I haven't used that word. So to distinguish the two of them, you say that an ordering a partial order is called linear order if, so think of this as a definition. If for every x and y in A, either x is related to y or y is related to x. Okay. Is that making sense? So like, just to give you an idea, of why this is not what happens with the integers, that you can try to do like some sort of like diagram for this ordering. So for example, like you can say, well, 1 divides 2, right? 1 divides 3, for example. So you can, let me put them vertically maybe. So yeah, maybe it's like, let's put 1 at the bottom. So you could say like 1 divides 2, right? And while 1 also divides 3. So you can make like an arrow from 1 to 2 and from 1 to 3 to make it clear that 1 divides either both of them, right? But then 2 divides 4, for example, and 2 also divides 6, right? So you could also make like some lines from 2 to 4 and 2 to 6 to indicate that that is happening, right? And at the same time, 3 also divides 6, right? And 3, what else? I mean, obviously they divide a lot more numbers, right? I'm just trying to show you some fragment of what we're looking at. And 3 also divides 9, right? But like, I don't know if it's, but like, for example, like 2 and 3 neither divides the other, right? So you cannot draw arrows connecting them. So the idea is like, if you think about like representing diagrammatically this ordering relation on the integers under division, there's no way to like arrange them just like on a line, right? Because literally that's what you would do if you had like this linear ordering property, right? When you're talking about less or equal than, right? When you have x and y, on the real line, you can literally just put them on the line and just draw the arrow this way, right? So there's a way to like draw this diagrammatically as a line, right? So what we're saying is that with the case of the integers and division, it's not possible to like sort out the natural numbers like so that they all fit like on a line where, you know, they're connected with like an arrow going to an arrow, go to an arrow, because they're just like a structure in a more complicated way. Is that making sense? And then just to give you another example before we move to something which is also interesting. Another useful example to keep in mind is like between sets. Another example of an ordering relation is that like here, like let's say, like let's think of x and y and set as sets. Then like you say that x is related to y if and only if x is a subset of y. So for example, the empty set, right, is related to everything, since the empty set is a subset of any set, right? But and then like, you know, if x is like 1, 2 and y is like 1, 2, 3, then in this case x is related to y, right? And it's not difficult to check that if you let x and if you take your elements to be sets, then this does give you like an ordering relation. You hear, I mean, you have to work inside a universe or whatever, but of sets, but like what I'm trying to say is that this, like the inclusion of sets, defines a post like an ordering relation. Right, because every set is a subset of itself. There's a reflexivity. If x is a subset of y and y is a subset of z, right, then x is a subset of z. There's a transitivity, right? And the last one is that if x is a subset of y and y is a subset of x, then x equals y as sets, right? And this is like the anti-symmetry. So yeah, do you think this is a linear order or not? Is this a linear order? What do you think? Again, like if you say yes, that means that any two sets can be compared under the inclusion. That means that for any two sets, one of the two must be included in the other, right? That's what a linear order would mean. So you may want to change your answer. Because if you have two arbitrary sets, is that the case that one of the two must be included in the other? What example? Let's say if x is, well, they're right. It's not order of their size. They're being ordered by, by inclusion. So for example, like if x is 1, 2, the set 1, 2, and y is a set 2, 3, right? Notice that x is not a subset of y, and y is not a subset of x, right? So both have like two elements. It's just that neither is containing the other, right? And so they cannot be compared. Like we're trying to compare element, like now we're comparing sets, saying that one set is smaller than the other if one is included in the other. So here, so this order is not linear. Is that making sense? Because like a linear order means that all, like if I had given you two arbitrary sets, you can always say that one is included in the other. So it's not, they're not being ordered by number of elements. They're just being ordered by inclusion. Well, I should write that in the chat. Is that okay? So, okay, and then there are like two, right, to finish today, like let me just give you a couple more definitions, which are very useful. These are actually very useful once you take real analysis, like if you take it next semester. So this is called like this, like at least upper bound and, or well, let's talk about upper and lower bounds. So L is a lower bound of a set B if okay, well, let me write it like this. Like here is A is a poset. And B is a subset of A. Here A is a poset and B is a subset of A. So L is a lower bound for A, for B, if for every B in B, L is related to B. Okay, so this looks a little bit weird how I'm writing it, but you'll see like in a second that this is not too complicated. This is very intuitive actually. So imagine that A, like just as an example, let's say that A is the real numbers and B is the subset, the interval 0, 1. Okay, so a lower bound for B, a lower bound for this set would be any number that's smaller than any number in this set. So this is like the, but here, this is like the interval. So a lower bound for B So what is a lower bound for this interval? Well, L would be like, for example, -1 is smaller than any element in the interval 0, 1. -3/2 also works. What is another number smaller than any element in 0, 1? Well, -5, for example, they all work, right? Etc. In fact, any lower bound, any number less or equal to 0 is a lower bound. Is that making sense? So a lower bound is just like an element that would be smaller than any other element. Here's another example just to make sure that this is making sense. So imagine that I had given you A to be the integers and B to be the set of even integers. Right? So what would be a lower bound for the set of even integers? What's a lower bound? Under the relation of division. Yeah, excellent. That actually will take us to the next point, but yeah, there can be more than one lower bound for now. Yeah, excellent. Yeah. Yes. But yeah, good point. So what is if you have the even integers, what would be a lower bound for the even integers under division? It would have to be an integer that divides any even integer, right? What would be an integer that divides any even integer? Two works. Is there another one that works? One also works. Perfect. Like since you're working with positive integers, like those would be the only two. But you see, like, so here, like, because 2 divides any even, these two numbers, because these divide any even integer. Is that making sense? And now this is related to the question of like, can there be more than one lower bound? Yes, but there's one that's kind of like the largest, and that's called the infimum. So the infimum, like the infimum for B is a lower bound So in other words, like the infimum is the largest lower bound. Well, we could, like, it's just that here, like in the example when I talked about division, I excluded the 0 because I didn't want to divide by 0, like, just for convenience, I didn't want to like, so here were like I wrote n, I'm implicitly excluding 0 to make our lives easier. But yeah, if not, you would have said, because right, it's not convenient to say that 0 divides an even number, actually. So like morally, the infimum is the largest lower bound. That's how you should think about it. Like, and that the usefulness of that is that that kind of singles out among all lower bounds the largest one. So like just to give you the examples, like if A, right, if A is like again the real numbers and B is the interval 0, 1, right? We gave a bunch of examples of lower bounds. What would be the infimum here? The infimum would be the largest of the lower bounds, right? So of all the lower bounds, which one is the biggest for this interval? The infimum of B should be the largest lower bound. And again, in the previous, here we had found some examples, right? We had found some examples of lower bounds here, which is the largest. I mean, and I didn't give you all of them, right? There were more. What of all these possible lower bounds, which one would be the largest? It's just 0, right? Excellent. Yeah. Because if you choose something slightly bigger than 0, you're already excluding elements in that interval, right? So 0 is the infimum in this case of that set. And this is like a concept that's very important in real analysis. So you'll probably, once you take real analysis, you probably start talking about, like the first thing you'll do is talk about this again. So like you would have seen it here. What would be the infimum of B in this case? It would be the largest of the of all the numbers of all the integers that divide the even numbers, which one was the largest, right? So we had some options for lower bounds here, right? And again, we are trying to find the largest of the lower bound. So which one that is? It's just 2. Good. So like the infimum here is 2. Is that making sense? And there's a similar story that happens on the other side. Like you don't have to look at the smallest one, right? Like you could have, I mean, instead of looking at lower bounds, you could have looked at an upper bounds. And there's like a similar story for everything, like of what we just said. So like an upper bound for a set for B is an element with the property that for every B in B, now B is smaller than the upper bound, right? So like just to continue with our example, if A is like the real numbers and B is the interval 0, 1, what is an upper bound here? An upper bound could be like, 1.1 or 2 or 3 or 10 or square root of 2, etc. Right? An upper bound for this set would be just like any element that's larger than the any element in the interval 0, 1. Is that making sense? Is that okay? And what like there's an analog of the infimum. The analog of the infimum would be now the smallest of the upper bounds, and that's called the supremum. So just to go back to this example, if you take A to be the real numbers and B to be 0, 1, right? We already mentioned like a bunch of upper bounds, right? All of these numbers are upper bounds, right? The supremum is the smallest of these that work, right? So what's the smallest upper bound that works for this case? Yes, someone answered correctly in the private chat. Right, because 1 is a number that's larger than any other number on the interval 0, 1. Larger or equal to. Right, you cannot choose something smaller than 1 because the moment you choose something smaller than 1, you are excluding elements from the interval. Okay, but so you should just think about the supremum as being like the up, there's upper, we had lower bounds and infimum. They can go hand in hand, and then we have upper bounds and supremum. So they're like go in pairs. Is that making sense? So like if you want to, right, supremum is the smallest upper bound. Yes, like if you want to think about it as a picture, like if you like in the case of real numbers, right? If you have like the number line, and you think of this as the set B, right? Then the supremum is kind of like, I mean, the infimum is kind of here, right? And the supremum is kind of here. So from that perspective, like, if you look at it as a range on the line, it does, like, the names do make sense. Is that okay? I'm imagining that the set B is not necessarily like an interval, right? Like it's just a bunch of stuff on the real line. So it's like in this picture, it consists of 3 parts, but like the idea is that, yeah. But yeah, supremum is the smallest upper bound, and infimum is the greatest lower bound. So let's just put it like that. Sup of B is like smallest upper bound, right? And inf of B is the largest or greatest lower bound. Is that making sense? So yeah, that's like the basic idea of like, I mean, like we'll continue after the Thanksgiving break. Like I have to add some examples or problems to the PDF, because like on the PDF of problems, we don't have examples about ordering relations. So I'll add some of them so that you can practice and be like, okay, check if this is an ordering relation, this is an ordering relation, what's the supremum, what's the infimum for a set, and things like that. Because this is also like a very important concept, especially in calculus, in real analysis. But like this is, I mean, it is very intuitive. It's just you just have to get used to like all the new names I threw at you, because there's a lot of new terminology. But like if you look at the definitions, I mean, like you really should have in mind this idea of like the formula in terms of the real line with the less or equal to. That actually helps a lot to understand these definitions. But as we saw, like it can also be applied to other situations like the integers and things like that, or sets. Like, okay, what's this, maybe before we finish, like for like this relation of, for like the relation of inclusion, where like you had like x is related to y if and only if x is a subset of y. What do you think would be an infimum in this case for like that, but for in this, like if we are looking at all the sets in some given universe, what would be the like the infimum of the universe of sets? It should be the kind of like the the smallest of the lower bounds, right? Oh, I should have I should have specified a little bit better, but like you should think of the empty set as some sort of infimum, right? Because like the idea is that the empty set, is a set that's containing everyone. So in that sense, it's less or equal to anything, right? But I mean, it is the largest of the smallest things. I mean, like kind of weird to say it that way, but like, there cannot be like the empty set is kind of like zero in this case, right? So if it is the analog of asking you what's the smallest integer, which would be zero, or the smallest non-negative number, which is zero. So empty set is working similarly here. But yeah, I should have said it like in a slightly better way. But like I'm just trying to show you that this concept of infimum of a supremum is kind of useful because it can be adapted to many different situations. Okay, but yeah, I'll add some examples and problems to the PDF of problems for our class, like throughout the break. Because again, in terms of topics, there's not that much left that I wanted to discuss in class. Like we're almost at a point where we can start flipping most of our classes to just like review sessions or something like that. So I'll have to think about what else I have to tell you, but I just probably will just add some more problems so that we can work on those during class. But yeah, like in terms of material, I don't think there's that much left that I wanted to tell you, so I'll have to think about that. We don't have that many classes left anyways, but yeah, probably we'll just do more examples of these kind of things. But I'll think I'll think about something. Is that okay? So yeah, if that sounds good, I that's more or less what I wanted to tell you for today. So thanks for coming. I don't know if there are any questions.
Sorry, Professor. I think the syllabus always said our final is from December 19th to December 23rd.
Oh, it doesn't say
Uh,
the date.
yes.
Oh, okay. I see. I see. Oh, I'm pretty sure of the day that I told you. I just have to double.
Okay.
I just have to double check then the time because I don't
Okay.
remember. But I do have it on the calendar, so I must be correct on that. I have it on my own
Okay.
calendar. It's just it's funny that I didn't have the time here. So yeah, let's see. I didn't put. What did I put on the box? Oh, you're right. Well, I mean, let me share. Oh no, like at least I see what you're saying. Like it does belong. You see, it does belong to this row.
Uh-huh.
It's under Tuesday, so this is correct. It is 20,
I got it.
but it is true that the time I don't think is it is true that the time is not yet on. I have to check if I wrote it somewhere else on the syllabus, but it may not be on the syllabus. So I'll need to check the time. I don't remember the time. It could have been 12 to 3 or something like that. Um,
Oh,
but yeah, as Kevin is mentioning, it's also on the Rutgers dashboard. And then regarding the exams, so I actually have to start grading them. I was planning on starting today and tomorrow. The things like I was doing like this other stuff for the multivariable calculus. Definitely I'll bring them on Tuesday, like of next week. But as I mean, I'll probably post like the grades I'll post the solutions and the grades probably throughout the weekend. As I had said, I didn't think it was like a good idea to post like give you the grades on the Thanksgiving break per se, but I'll probably post them um on the on the on the Canvas side. Well, do you mean like make up the exam for the final? Well, I mean, I have to check if there's like a specific date that the makeup is supposed to be, but if not, I mean, it would just have to be a different day, either of that week or, I mean, I suppose. So I don't
The
think.
makeup the makeup exam will have different questions with the final exam, right?
Yeah, I suppose like it also right, like in principle, yes, like there's no promise that the exam would be the same. Yes. It would have to be a different exam, correct? I guess so. Especially if the makeup is not, yeah, I mean it is better because it's a final, yeah. And especially if the makeup is not like the next day or something like that. I mean, again, I don't like our class is very small, so I don't think that like the makeup has to be on a specific day. I have to check that, but yeah, like in principle, assume that the makeup would be a different exam. Yes, correct.
Thank you.
Yeah. But again, like I just have to check how many people are like supposed to need to take the makeup and things like that. Because it would be ideal not to do like 2 or 3 different makeups, like because that would be 2 or 3 different exams. So if there's a couple, I mean, I don't think that there would be that many of you that need to take the makeup anyways, but yeah, I mean, yeah, the final would be in person, correct? Yeah. I mean, like, right. Yes, this is true also. Anyone else? Any other questions? Okay, yeah, I'll upload the video soon and the notes like sometime tonight. And enjoy the break. If something comes up, you can email me. But yeah, I'll send like I have to update some things for your class, but I'll hope to do that throughout the this week in that case. Yeah, thanks. Happy Thanksgiving to you as well. Bye.